fractal image compression using the hardware-software co-design methodology. First, we want to know what is meant by fractal image compression. This fractal image compression is a lossy compression method for digital images based on fractal. This method is best suited for natural images and it will give the part of an image which will often resemble other part of the same image. However, this is not been used in large amount of populations because of the complexity in the tool. On the other hand, the development of VLSI technology allows the creation of complete systems inside a single chip called SoC. So here in this paper, overall we are going to discuss about the hardware-software co-design on a fractal image compression, which improves the compression time and obtaining the acceleration factor between 6.6 and 8.5. This whole system is built on a SoC, and that SoC is based on FPGA. So now we are going to see fractal image compression.
The basic concept behind fractal image compression is to take an image and to express it as a locally integrated function system. To do fractional compression, the image is divided into subblocks. For each block, the most similar block is found in a half-size version of the image and stored. This is done for each block. Then, during the decompression, the opposite is done iteratively to recover the original image. In order to evaluate how similar are two images, we compute a distortion. The most common distortion criteria are root mean square error (RMSE) and the peak signal to noise ratio (PSNR). Hardware and software partition. The partitioning of the application can be done once. We can obtain its performance profile, which could be obtained with software tool drive GPRF.
Here, the performance profile is functionally divided into three groups: file, read and write, control blocks, and pixel calculation.
This involves analyzing set program to detect how its execution time is distributed between its functions and procedures. With this, we can see which part of the application are used more often or are the most time costly, or therefore we can determine the parts that could stay in software and the parts that could be implemented in hardware.
By this, we can describe about the transformation and comparison unit. So now here we are going to see the diagram of organization of TCU. The TCU means transformation and comparison unit.
The transformation and comparison unit receives the range and the domain blocks to be processed through a 32-bit input port called in data. Each of the blocks divided on 16 frames of 32-bit. The 8-bit input port in command receives a control word from the processor. In the 4-bit output port out SIM, we obtain the identification of the transformation of the range block with the least distortion with respect to the domain block. At the same time, the output port output data shows the value of the distortion. The signal done coming from the control indicate the end of the processing and can be used to send the interrupt to the processor. Control unit. The data part is formed by 3 5 and 12 bits register, an arithmetic unit and the 3 routing units. The range block and the domain block register contain the range, the block and the domain block respectively, while the reflected range block register contain the transformations applied to the range block. The arithmetic unit AU computes the absolute value of the pixel difference accumulating the results in AAC. AAC is accumulator. The routing units 001, 010 and 100 take the pixels from the range block register to the range reflected range block register, affecting a spatial relocation.
So here we are going to see the state diagram of the transformation process. Here the transformation control unit stays on a waiting state HD until it receives the activation signal E.
The state HD is used to assign the initial value for block processing. In the state RIN, the necessary values to process each transformation are initialized. The state BR determines the transformation to be applied depending on each transformation. It moves to one of the states 001, 010 or 100. For example, to complete the transformation 5, that is 101 binary, it will be the necessary to pass the first to the state 001 and then to the state 100. The state S and T, SHR take care of the calculation of the absolute value of the difference of each of the 64 pair of the pixel that forms the transformer range blocks and the domain block. The calculation is performed by shifting the registers accumulator and the minimum distance is performed. In this case, the value of the accumulator is less than the value of the minimum distance on the state. The values of the register, minimum distance and final symmetry are updated, storing the identification of the transformation with least distortion. The 4-bit counter symmetry identifies the transformation performed. If its value is less than 8, then it moves to the state RIN, otherwise processing is done. We show the register and signal that forms the interface. For example,
now we are going to see the hardware and software interface for this project, that is Fractal image compression on SOC. This SOC is based on FPGA. So we are going to see the interfacing of hardware and software in this diagram.
For example, the 32-bit register bus data was connected to the in-data port of the TCU in order to receive the data, while the register IP2 bus data is used for data output from the TCU. At the same time, it was necessary to add the control signal to integrate the TCU into the communication protocol of the peripheral bus.
So after the finishing of the hardware and software interface, we are going to create a computational system on the FPGA with the embedded PowerPC 405 processor, and the whole system is kept inside a single system on chip for writing the files, read, write, the control block, everything. We are going to use a FAT32 file system, and so many other orders are used and form a single system on chip. So here we are going to see the comparison with and without transformation and control unit. So here some tableau problem is given without and with transformation control unit.
As we can see on the results, the performance of the coding an image using the fractional image compression algorithm improved substantially by integrating a hardware component on the application. The added component computes the most time costly part of the application, and this was identified through the analysis of the application's performance.
So as we can see this by just saying that without TCU and with TCU the time is decreased. So without TCU the time is 52 and with TCU the time is only 7. So by this we can see that the system is efficient by the use of hardware and software co-design. Therefore,
this we can show that it is possible to accelerate the application that require intensive computations through the use of the hardware software co-design. Thank you.